let's make a start in. So welcome to the talk. Just before we start, there is a Git repo containing all the code samples that I'm going to be showing you, and we have also done a PDF of the slides. Yeah, so the slides and all the code will be made available immediately following the talk. So good afternoon. My name is Garth Gilmour. I work for a company called Instill in Belfast. Instill are a software development company, or rather about 80% of what we do is software development and 20% is training, consultancy and professional services. So that's the bit that I'm in charge of. And that's my partner in crime who was due to be with me in front of you in person. So that's Ryan Adams there. So let me start off by saying we're sorry. We are very, very sorry. We had 1 hour to go before the taxi was going to pick us both up, but new regulations were being introduced. So we were flying out of Belfast and flying back in through Dublin, and the UK and Ireland were introducing new regulations, and everything just got too scary and complicated. So we are gutted that we cannot be with you in person. Very, very sorry about that. But let me do the best I can. Yeah. So introducing the talk, we're here to talk about lies told by the Kotlin compiler. Okay, so why do we need lies? Yeah, well, we need lies because Kotlin is an awesome language, as you know. It provides us with many wonderful features, and these features don't exist on the underlying platforms. Yeah, so for example, reified generics, don't exist in the JVM and so on. So there are many wonderful features that Kotlin gives us, and we need the compiler to emulate them for us. Okay, so the Kotlin compiler pretends that things exist that don't actually do. So the compiler is lying to us. Yeah, and initially we don't care what's truth and what's fiction. Okay, we don't care what is a lie and what is reality. But as we get more experienced, as we start worrying about interoperability or performance or multi-platform or any of these things, then we need to learn how to distinguish between what is a lie and what is reality. Okay, so lies can be a good thing, yeah, because whenever the compiler tells us enough lies, it moves us up to a new level of abstraction. And wonderful quote here, but the purpose of abstraction is not to be vague, but to create a new level at which we can be absolutely precise. So the Kotlin compiler is trying to lift us up to a point where we can be more precise and productive in our thinking. But as I say, eventually we will need to know the truth. Yeah, so for interoperability and performance, if nothing else. So how do we find out the truth? Well, we find out the truth by using a decompiler. So nothing is ever hidden in software. We can always dig in and see what's going on. Even if somebody has used an obfuscator only obfuscates. It can't completely hide things from us. So whenever it comes to Kotlin, we've got two choices. So the first choice is we can go into IntelliJ and we can say tools and we can reverse engineer. So we can take any Kotlin code and we can have a look at the bytecode. And then from the bytecode, we can we can press that decompile button, and that will generate some Java that we can look at. So we can take any Kotlin code and we can reverse engineer the Java equivalent. And this is a really, really good way to learn. So many, many years ago, this is the way I learned C#. If anybody's done .NET, you'll know in .NET there's ILDASM. So ILDASM can show you the underlying IL generated from any C# code. And that's a really interesting way to learn the language and see how the advanced features work. So learning a programming language by decompiling the code is a really interesting way to learn. So you've got the tools that come with IntelliJ, but those only work to a certain level of complexity. Whenever you need more detail than that, there's javap. So javap is the bytecode decompiler that comes with the JDK. So you give javap a class file, and it gives you the declarations of all the things inside the class file. There are a bunch of different options. You can use -p to show absolutely everything. You can use -c to see the bytecode instructions and so on. It's a wonderful tool. Yeah. So if you're not acquainted with javap, I would really encourage you to go out and play with it. It's really good fun. So we're going to look at three different levels of lies, okay? We're going to look at lies told within the language itself. Then we're going to look at the lies told whenever suspending functions and coroutines are being implemented. And finally, we're going to look at lies within Jetpack Compose. Yeah, so three different levels of deceit. So let's start out with the language, and let's start out with something really, really simple. So as you know, Kotlin gives us free functions. We don't have to worry about declaring static methods inside classes. We have free functions, and those make our lives so much easier. So let's say we've essentially done hello world here inside program.kt. Most of these examples are going to assume we're in a file called program.kt, and we've got the Kotlin version of main where we don't have to pass in the args, and we're invoking the free function print message. So if you run that through the decompiler, what are we going to get? Well, you see that these things are actually static methods. So free functions don't exist in the JVM. So when you run it through a compiler, you get a class generated named after the file. So our file was program.kt. So we get a class generated called program.kt. And inside there, we have three static methods. One for the traditional Java main. That's there to invoke the main that we wrote, which took nothing, and that's there to invoke print message. So the free functions that you write get converted into static methods. So let's make it a little bit more interesting. Let's say we nest it. Okay, so let's say print message is only called within main. So then the best thing to do would be to nest the functions, and that's another wonderful thing that we get from Kotlin. Yeah, this is actually the only feature in JavaScript that I like, the ability to nest functions. That's where I first met it. So what does the decompiler do with that? So again, we get two versions of main. We've got main that takes a string, and then we've got the main that we wrote. And you can see inside there from the bytecode, we're going out and we're invoking the static method main $print message. So our nested function got converted into a regular static method, and the name of that is the name of the outer function, the dollar, and then the name of the inner function. So again, we're being lied to, but in a nice, productive way. So this, of course, raises the interesting question: what happens if we had two nested functions called print message? So what happens if I have two functions called main or demo or Fred or whatever it happens to be, and each of these has a nested function called print message? What happens then? Well, let's try it. Yeah. So you see here we've got main. And inside main, we've got demo taking an int, and we've got demo taking a double. And we're going to invoke both of them, but each of them will contain a nested function called print message. So whenever I did this, I kind of expected that there would be name mangling going on. So what we would have, we'd have a static method generated whose name was demo $int $print message. So we the function signature would in some way be involved in the generated name given to the inner function. But it's not quite that. So we get our two functions called demo, one taking an int, one taking a double. And then you can see inside there, we've got demo $print message, and then we've got demo $print message -0. So it's simpler than we thought. Okay. So the first inner function called print message, it's just print message. The second inner function called print message, it's going to be print message -0 and so on. Okay, so it's done in the simplest possible way, but whenever it comes to performance and so on, well, simplicity is a good thing. So moving on, let's talk about a lie that we all understand. Let's talk about a lie that as Kotlin developers, we rely on every day. And that's the lie that there is such a thing called a primary constructor. It's the idea that you can merge together the class declaration with the constructor declaration. So you see here we have a person, and a person has a name and an age. And we also have a private field called full name. And in an init block, we're going to set that to the name plus Jones, whatever that happens to be. So if we go out and look at this in Java terms, well, you'll see that we get final fields, and then we get a constructor generated. And inside the constructor, we have all the standard initialization code, the code required to take the values from the parameters and set them in the fields. And we also have the code that was placed inside the init block. So the Kotlin compiler is lying to us, but in a really, really helpful way. It's giving us this illusion that we have a primary constructor, whereas what we're getting generated is just a standard Java fields and constructor arrangement. Another lie I particularly like, extension methods. So let's take our person class and we'll extend it with say hello, just like this. And let's take the string type and extend it with times. So whenever you're maintaining and working with other people's code, as you know, extension methods are absolutely brilliant for raising the level of abstraction and making things more convenient and so on. But again, it's just a lie. Yeah. So instead of opening up the class called person and adding a method called say hello, we've got a static final method that takes a person. Instead of opening up the string type and adding a method called times, we've got a static final method called times that takes a string and so on. Yeah. So all that's happened is that we've got a standard function. Yeah. And what's being inserted into the function is the object that we're trying to extend. So it's just a conjuring trick. It's magic. Yeah. It's just a very nice bit of deceit performed by the compiler on our behalf. Okay. Another one that's very useful to know, especially if you're going to be debugging, is how destructuring actually works underneath the hood. So person class again, but this time it's a data class. So as you know, whenever you declare something as being a data class, lots of extra stuff is generated for you. And we're creating a person object here, and we're storing the name and age into X and Y. So how is this actually implemented? Well, again, we destructure, and we can see that as well as all the other goodness that we get, like a copy method and hash code and equals and so on, we also get methods called component 1 and component 2. And if we look at the bytecode for the main method, you can see that these are being invoked. So inside main, we're going up to our person object, and we're invoking component 1 and component 2 and so on. So destructuring sounds complicated, sounds difficult, sounds like a hard thing to do. It's actually implemented by the compiler in a really boring way. Yeah. So if we had 5 properties on our data class, we would have methods called component 1, component 2, component 3, component 4, and component 5. Yeah. And these would just be the methods that would get invoked on our behalf every time we destructure. Okay, so again, it's very simple, but simple is good. Simple is fast. Yeah, simple is what we want. Moving up the complexity ladder, let's look at something a little bit more complicated. So let's say we've got some object declarations. So we declare an object called math with an add method. So what's the compiler going to do with that? Well, if you look here, you see that it's going out and it's implementing the singleton pattern from the game of 4. Yeah, sorry, the gang of 4. Yeah. So what we have here is we've got a class called math. Yeah, and then inside there we've got static final math instance. Yeah, and we've got a static initialization block. So whenever this class gets loaded into the virtual machine, we create a new math object. We run the math constructor. Remember that in the bytecode, constructor functions are turned into functions whose name is angle brackets in it. So we create a math object, we run the math object constructor, and then we store it inside the static field. Okay, so it's the standard gang of 4 design pattern, which is being implemented on our behalf by the compiler. And we can see that in main, where before it goes out and calls the add method, it retrieves the value from the static field called instance. So it's just the singleton pattern in disguise, implemented for us by the compiler. Very similar for companion objects. Let's say we've got a class called employee, and we want to be able to build an employee object with the department hard-coded as HR. Or we want to be able to build an employee with the department hard-coded as IT. So again, singleton pattern, but now the name isn't going to be instance anymore, it's going to be companion. And the type of the generated class is going to be name of outer class $companion. So it's the same pattern as before. We've still got a static instance, yeah, but now the name has been changed, yeah, but same idea. And then my absolute favorite example of compiler deceit enums. Yeah. So how do enums get implemented? Well, enums are classes in disguise. And this is somewhere the Kotlin compiler is actually a little less deceitful than Java, because in Java, you would just say enum color. In Kotlin, of course, that class gets thrown in. And that's to give us a clue as to what's going on. So if we decompile this, we can see that color extends the base class enum. And then for every member of the enum, we have a static final field. And we also have an array that contains all of the color objects. So as with previous patterns, we've got a static initializer block. And inside this static initializer, we're going to create all of the objects and store them inside the fields. Yeah. So remember, we've got a static final field of type color for each of the color values, red, green, and blue. So inside our static initializer block, we create a color object and store it in the static field. We create a color object, this time for green, store it in the static field. We create a color object, this time for blue, store it in the static field. And then finally, we populate the array $values. And this is a performance enhancement, just so that every time we say color.values, it doesn't have to recreate the array from scratch. You know, that would be bad for performance. Instead, it'll be there already. It'll already have been created whenever the class was loaded in. So happy days. Okay. Another complicated one, lambdas with receivers. Woohoo, tricky. Yeah. So let's say we've got a person class again, and then we've got a function called demo, and this takes a person object and a lambda with receiver. Okay. So this is a lambda function that takes nothing and returns nothing, but inside there, whenever you use this, it's going to refer to a person object. And you can see there, we take the person object and we apply the lambda to it. So we've got our function called demo that takes a person. Then we've got a lambda. Inside the lambda, we're going to add 10 to the age of the person and print them out, you know, and you can see what's happening there. So what's going on whenever we disassemble is we see that instead of this syntax here, which is very nice and convenient and easy to understand, again, it's a lie. What we have is we have a functional reference. Yeah. So we have a type called function1, and this takes two type parameters. There's one type parameter for the receiver and then one for the return type. And then if we look down here, we can see that we're going to have a generated class called program kt $main$1, and that will have a static field called instance. And that's what we're actually working with. So the lambda with receiver will get converted into an inner class. There will be a static instance of that inner class, and that's what we're going to be retrieving there. So there's a bunch of these interfaces. There's function, function1, 2, and 3, and so on. And they all have an invoke method, and they all use generic types. And type parameters, I should say. And the first type parameter is going to be the type of the receiver. So hopefully, in this first bit of the talk, I've convinced you that there's a lot of lying going on, you know, whenever your code is being compiled. But that's a good thing, okay? So let's go to the second type of lies, and those are lies told with suspending functions, okay? So whenever people get taught about suspending functions, they're told that a suspending function is a function that can be paused and then resumed. Yeah, but are they? Are they really? You know, do suspending functions really suspend? Are they magic functions which can be paused and resumed? You know, so let's write a little RESTful service to determine if this is true. So we'll use REST because that's the most common use case for suspending functions. So let's order a RESTful service for ordering breakfast. Yeah. So a little bit late in the day, I thought this talk might be earlier. Yeah. So what we'll do is we'll write some entity classes. Then we'll write a server, then we'll write a client that uses suspending functions. So first of all, for breakfast, let's have our beverage. You know, so every beverage will have a size, every beverage will have a type. Yeah. So we've got a serializable class called beverage that has a type and a size, and you can drink it. And then we'll have a class called food. So every piece of food will have a name, it will have a serving size, and we'll store whether or not it is chocolate. Everything is better with chocolate, but it might not be there. So we'll have an eat method. And then finally, we'll have a breakfast class. So breakfast will be made up of a beverage and some food, and we'll be able to consume it. So here's our server side. We're going to be using KTOR, of course, because it's a Kotlin conference. So we'll do some routing. So we'll say, okay, if a GET request comes to /breakfast/beverage, calls select beverage. If a post request comes to /breakfast/food, well, we're expecting the body of the request to contain the beverage, and then we'll call select food. So here's our implementation of select beverage. If we're in France, then we're going to be having a cafe au lait, otherwise it's Americano. If it's before noon, then we'll have a large because we need it. Otherwise, we'll have a medium because we want to get some sleep tonight. So we'll build and return a beverage. And then whenever it comes to selecting some food, we'll take the beverage. And if the size is large, we'll have 3 of whatever, otherwise 2. And if it's cafe au lait, then we'll have croissant. Otherwise, we'll have pancakes. So that's our server side. Here's our client side. So in our client side, we've got our main function, of course, and we're going to go out and call run blocking, which must only ever be used in demos, and not anywhere else. And then we've got a helper function called print in detail. So print in detail is going to print a message along with the current time and thread. So if we look at the output, we can be sure that we're switching threads. Build HTTP client does what it says on the tin. So we're going to get our HTTP client, and then we're going to order breakfast and consume it. So here's our print in detail, standard stuff, don't need to worry about it. Here's our method for building the HTTP client, standard stuff, don't need to worry about it. Here's the function for ordering breakfast. So you can see here we take our client, and then we're switching to the IO dispatcher, and we're going to go out and order our beverage. And once we've got our beverage, we'll use that to order the food. And once we've got the food, we'll build and return a breakfast object. So this is the function that we'll be decompiling in a minute. But just to show you, this is how order food works. Just use the HTTP client to send a post request. This is how order beverage works. Just use the HTTP client to send a get request, standard stuff. So all of that is just to build us up to this point here, where we've got a working function called order breakfast. And this is a suspending function, which calls 2 other suspending functions. So let's disassemble it and let's see what's going on. Okay. And if you disassemble any suspending function like this, you'll get this arrangement here. So what we've got is a switch statement where we're switching on a label field. And that switch statement is inside a labeled break. So we've got this label 17 brace. So inside the code there, if we were to say break label 17, that would take us out of the whole thing. Okay, so this is the really big lie. Okay, this is the whopper, as we would say in the UK. Okay, so at the end of the day, it's just a big switch statement inside a labeled block. Okay, so whenever you have suspending functions, what gets produced by the compiler is just a big switch statement inside a labeled block. Okay. So let's look at it in a little bit more detail. You see, we've got this variable called var4, and we're setting it to get coroutine suspended. Well, what on earth is that? Okay. Well, if you dig into the coroutine specification, it'll tell you that there's this special value called coroutine suspended. So let's say we have suspending function A, which calls B. Okay. Well, B can signal to A that it wants A to suspend. So suspending function A calls suspending function B. And B is going to do one of 2 things. It's going to return the actual result, or it's going to return this special value coroutine suspended, and that will be a signal from B to A that B wants A to suspend. So here, var4 is going to contain this special coroutine suspended value. And we're going to start off at case 0. So we're going to switch on this thing called label. And by default, the label will be set to 0. So what are we going to do? Well, we're going to set label to 1, and then we're going to call order beverage. And the value that comes back, we're going to store in this special variable called var 10,000. Okay, I've always wanted to write suspending functions with variables called var 10,000 and so on, just to see what happens, But var 10,000 is special, because it stores the return value from all the suspending functions that we're calling. So we call order beverage, we get back the return value, and we compare that to var4. Remember, var4 holds coroutine suspended. So if the 2 are equal, well, then that means that the function we're calling wants us to suspend. So what do? We just return. So there's the big lie, okay? So a suspending function is not a function that gets paused and resumed in some strange magical way, Instead, a suspending function is just a regular function which returns and gets restarted. And every time it's restarted, it uses this label to jump to the appropriate point, okay? So we pick up the processing wherever we left it off, okay? So this is referred to as the continuation passing style, okay? Because the label and various other bits of details are stored in an object referred to as the continuation. So let's say we call order beverage after we've been restarted and it actually returns the beverage. Well, what are we going to do? Well, we're going to store the beverage in a special field called $0. Okay, so this, like the label, is being stored inside the continuation object. Yeah, this is how our state is being managed. So whenever the function returns, the continuation will still be there, and we can call the function again, jump to the appropriate label, and restore the values from the continuation object. So we'll take the beverage and we'll store it inside a field of the continuation, and then we'll go out and order some food. And again, the value that comes back is stored in this special variable var 10,000. And if that's equal to the magic value that says we should suspend, then we return. Again, a suspending function is just a function that returns and gets restarted. So let's say our order breakfast function is called again, and this time the label is 2. So we'll get out the beverage, we'll get out the result of calling order food and put it into var 10,000, and then we'll say break level 17, okay? So remember, sorry, break label 17. So remember, break label 17 is the magic thing that exits the entire mechanism of the suspending function. So that will take us to this point here. Yeah. So we've now jumped out of label 17. So we can get the food out of var 10,000. We already got the beverage earlier. So now we can build and return our breakfast object. Okay. So whenever it comes to suspending functions, j'accuse, they're not really any magic, okay? They're not special functions that get paused and resumed or anything like that, So a suspending function is not a function that suspends. It's just a function that returns and then gets re-invoked, yeah? But we use these continuation objects to hold labels and intermediate state, okay? So if you had a suspending function that was calling 4 other suspending functions, let's call them A, B, C, and D. Yeah. Well, the intermediate results from A, B, and C would be stored in the continuation object as well as the current label. And the switch statement ensures that we resume processing at the current point. And the labeled block around the switch statement, well, that just short circuits processing whenever we've gone far enough, whenever the job of work is done. So it's all a big lie, okay? So we've seen lies told within the language, yeah? We've seen lies told by suspending functions, yeah? Let's have a think about lies told by compose, okay? So I know that there have been some earlier talks today about jetpack compose. Don't want to repeat too much of that. I'm sure you already know the story. Whenever we're building Android, applications, we use an XML layout format that absolutely everybody hates, So that is being replaced by Jetpack Compose, which is a really, really nice DSL. Yeah. And it doesn't just work on Android, it now works on multi-platform. Version 1 released today. Yay. Okay. So you can now use this in production as of today. Yeah. So Compose doesn't just work on Android apps. There's also a desktop version and there's also a web version as well. So anytime I have a UI framework, the first thing I go out and do is write a little calculator, So in the code to accompany these slides, there's a little calculator demo for Compose. Very simple, very basic, just gives us an idea of what's going on. So Compose is implemented as a DSL, but it isn't what you would call an internal DSL. It doesn't just use the features of the Kotlin language. There's also a compiler plugin required as well. Okay, so that tells us that we're being deceived, that there are many, many lies being told. So here's my very simple calculator. This is the setup. we've got a window, and inside the window, I'm setting up the state that we need for the calculator. And then we've got the DSL bit down here. And we have a bunch of components, and a component in compose is just a function that's annotated with composable. So we'll have a composable function for the theme that we want to apply, the look and feel. We have a composable function for a text box. We have a composable function for a number containing, sorry, I should say a button containing a number. Yeah. And then we want to put those in rows. So we'll have a component for that. And we want to put the rows into columns. So we'll have a component for that. And then we want to have a component for an operation button. So this is a button that's going to have plus, minus, divide, whatever, you know, and perform the appropriate operation whenever you click on it. And then we want to put those in columns. Yeah. So we'll have a widget for that as well, an operation button column. And you see there the different operations that we're going to have. So easy peasy. So let's say we decompile this, and let's see what happens. Okay, so again, we're going to have a function called display text, and we're going to be annotating this with composable. And inside here, we're saying that we want a text field containing the supplied text with this style and so on. Well, whenever we look at what gets produced, it is just a function. You know, it is just a Kotlin function, but it has two special inputs. There's an input called composer, and there's an input of type integer. Okay, so what are these? Yeah, well, the composer object is the thing that builds the logical tree of widgets. So every GUI library I've ever used ever has represented the GUI as a tree of widgets or controls or whatever you want to call them. And even if it's not represented in memory as an actual tree, it's a logical tree. You know, that's how we think about it. So the job of the composer object is to build the tree of widgets. And then what's the integer for? Well, if you think about it, this display text composable function or widget or control, whatever you want to call it, I can use this in any number of places. So I might use this in any number of places in my GUI, and the text might change in any of those places, or it might need to be redrawn in any number of those places. So if I've used this widget in 5 separate places, there's going to be 5 different call sites. Yeah, and we need a way to be able to disambiguate, you know, those different call sites. So what's going to happen is that every time display text is invoked, a unique number is going to be passed in. So that number will uniquely identify the call site. So whenever I'm building my logical tree of widgets, whenever I'm building my GUI, if I've used the display text 5 times, well, then 5 different numbers will get passed in. Okay. So again, that's repeated for every widget. So if we disassemble the whole lot, we'll see that all of my widgets just get compiled into static methods. As we've already seen, that's what the compiler does for free functions. And then inside there, there'll be always these 2 extra parameters, the composer parameter and the integer parameter. Yeah. And then what are these being used for? Yeah, well, as I say, they're being used for what's called positional memoization. Whoa, big word, you know. And all that means is that the underlying data structure needs to remember each call site. You know, it needs to know each specific instance where the function was applied. Yeah, and because of that, we can do recomposition. So we can rebuild any bit of the GUI at any time. Because whenever an event occurs, we don't want to have to redraw the entire shebang. We only want to redraw part of it. And the way this is implemented is through a data structure that they call a slot table. And this is just something I'm just learning about myself at the moment. You know, I've just read the books and seen the talks, same as you folks. Yeah. But what it's doing is it's building up this data structure. And this data structure is going to be made up of groups of values. Yeah. And each group is going to be identified by these integers that we were talking about. So let's look at the bytecode for our display text. So just to go back a wee minute, remember that this is what we wrote here. Yeah, this is what got generated by the compiler, and inside here there's going to be loads and loads of bytecode. So let's just have a look at some of that bytecode. So you can see we go up to our composer object and we invoke start or restart group, and we pass in this integer value. Okay, so remember, this integer value uniquely identifies the call site. So we're going to go there and we're going to invoke that, and then we can do other things, and then whenever we're done, we're going to end the group. Yeah. So if we had nested components, yeah, they could go out and add groups of their own as well. But it's this data structure here, it's this slot table, which is being built up underneath the hood. And that's the thing which is used to create the tree of components. And that's the thing that actually gets rendered on the screen. Okay. So there's a huge amount of deceit going on. Yeah, a huge amount of work is being done in the background to enable this illusion that we have composable functions that we can just combine together any way we like to get a tree of controls. Yeah. So here's two excellent sources that I would recommend, yeah, if you want to find out more about how all of these works. A really, really good talk from Kotlin Conf, and a book that's been recently published on the internals of Jetpack Compose. Yeah, but of course, there's a lot more coming out now at the moment as well. So some conclusions, yeah. And just before we do the conclusions, Baron Noir, amazing show. Thank you so much, France. Okay, just finished watching this, all 3 seasons, absolutely brilliant. Any fans? Give me a hands up if you're a fan. Any fans in the room? Couple? Yeah, very good. Yeah. So yeah, so lies are everywhere, okay? And lying can be a good thing, okay? So the Kotlin compiler lies to us in order to provide advanced features, yeah? And in order to ensure consistency across all the different platforms that the language supports, yeah? So there are small lies told to us in the language itself. There are bigger lies told with suspending functions, and the whole desktop compose and so on, well, that's telling some whoppers, you know, but that's a good thing. So all these lies let us work at higher levels of abstraction, which is a good thing. Yeah. And most important of all, they get us home at 5 p.m. Most vital point of all. Yeah. Cool. So that's my talk. Thank you so much. Let's open the floor to any questions.
Thank you very much. So who wants to ask Garth a question? Don't be shy. He's far away. He can't touch you.
I can't get you from here, yeah.
No, pas de question, no question. Okay, so Garth, looks like you were perfectly clear and everything's all right.
Cool. So just to say, remember, all the code and the slides will be made available. So feel free to reach out to me on social media if you have any questions afterwards. Thank you very much indeed.
Thank you very much, Garth. We really appreciate you taking the time to do this.
No, of course. I'm very, very sorry I couldn't be with you. Bye-bye.
No problem. Bye-bye.
Bye.